So recently I've been doing a lot of work with a 4-quadrant multiplier or a ring modulator, and I have been hinting that I'm trying to use a ring modulator to emulate what happens inside of a triode in just an ordinary gain stage. It doesn't seem like those two things should really go together. A ring modulator sounds nothing like a tube gain stage, but there's a mathematical function that the ring modulator will do that I need in order to solve the equation for a triode gain stage. Let's take a look on the bench. I want to step through all of the mathematics, and then we can pick up and carry on with the ring modulator. Okay, so stick with me. It's a lot of math, but it's worth it in the end. All right, let's go to the bench. So what I have here is an older Russian tube. This is a 6N2P dual triode. It's related to the 12AX7, but the mu factor or the amplification factor for this Russian tube is only about 80. For a 12AX7, it's as high as 100. So it's not quite as powerful in terms of amplification, but it's nearly identical. And I also happen to have a box of these, so they're easy for me to experiment with. All of this analysis is in an Excel spreadsheet. I'm going to make that file available for you guys. Link in the description. Here's the process that I went through. I took an image of the grid curves from the data sheet, and I overlaid on top of that a plot in Excel, making sure that the origin was lined up as well as the extent of the horizontal axis for the plate voltage, going from 0 and stepping up to 440 volts, and the vertical axis for the plate current ranging from 0 all the way up to 4 milliamps. Then the process was going from 1 volt, then to a half, then to 0, and stepping up in half volts all the way up to minus 4.5 volts there. And one by one, picking a point that lined up with these grid voltage curves. And so once I had one complete curve, I went to the next one, did another series of points lining up, usually within 1 or 2 decimal places. So I have this series of curves now, and you can see them overlaid on top of the image below. So this is the table of data that I collected for each one of those grid curves. Here on the left, this is my plate voltage going from 0, 10, 20, 40, 60, and so forth, up to 420. Each column is one of those grid curves. This one here on the left is the grid voltage is 1. The next one over is for a half, then for 0, minus a half, so forth and so on, all the way up to minus 4.5 volts. The numbers that are recorded here for whatever the plate voltage is in that horizontal axis, I record the plate current in this column of numbers. So once I have a series of points for the 1 volt grid line, I go to the next and record my series of plate current for the corresponding plate voltage. This is a tedious process, but once I have all of these things filled out, I have my series of points and map the plate voltage to a plate current. Next step in Excel is I want to derive some coefficients for those curves. And in particular, I want to generate coefficients for a second order polynomial. Excel gives me this function to generate these constants for a line of best fit, but it's giving them to me in an array. So I have to use this index function wrapped around that and then index which one of the constants I want to retrieve. So now I have a series of coefficients for a polynomial for every one of those grid voltage lines. Step number 3 in the process, we're returning to the curves for the triode. I have a generic gain stage here, and I have omitted the coupling capacitors coming into the grid and coming off of the plate here because they're not critical for the calculations that we're doing at this stage. So the first choice that I've got to make is deciding what voltage I'm going to run this gain stage. So my B plus voltage, that's going to be my maximum anode voltage, or my VA max. And I've chosen a value of 250 volts here. So that gives me that point right here on the horizontal axis. The next decision to make is a value for the plate resistor, and I've chosen a pretty generic value of 100K. To calculate what the cathode resistor is going to be, I'm using a golden rule where the cathode is 1/66th the value of the plate resistor. So 100K divided by 66, that gives me a value of about 1.5K. Now that I know a voltage and these resistance values, to calculate the maximum current, I just use Ohm's law. I've got a voltage, I've got a resistance value, and I calculate what the current is coming through these two resistors. So my maximum anode current is going to be the maximum anode voltage divided by the sum of the plate and cathode resistors. And in this case, that winds up being just under 2.5 milliamps. So I've got a straight line defined by these 2 points, the maximum voltage and the maximum current. That is my load line. Now the operating point for my gain stage here is probably somewhere around in the middle here. So with my gain stage defined and my load line drawn, now I need to know what the equation for this load line is. It's just a straight line, so I need a slope and an intercept point, and I can calculate the current at any point for any voltage along that line. And I have that equation here where my current is equal to the slope times the voltage plus the intercept point. My intercept is just the maximum current. The slope is a negative maximum current divided by that maximum voltage. Step number 4, recall how for each one of those grid lines, I have this second order polynomial with the coefficients, and for the load line, I have this equation where, given a plate voltage, I can calculate the current at the plate along the load line. What we need to know now is the intersection of that load line to the grid lines. To do that, we set one equation equal to the other, and we put all of the terms on one side of the equation, and it's equal to 0 now. Well, now we've got a quadratic equation, and we can use the general solution for a quadratic equation where x is equal to negative b plus or minus root of the quantity b squared minus 4ac, all divided by 2a. And a in this case is going to be our constant C2. B is going to be constant C1 plus the maximum current divided by the maximum voltage from the load line. And C is going to be our constant C0 minus the maximum current from the load line. And what I've done in Excel is I've gathered up all of the coefficients for the grid lines. I've pre-computed A, B, and C for that intersection with the load line, and I've drawn out a value of the plate voltage and current at those intersections. So it's not an exciting step, but it's critical for step number 5. I'm going to do the same derived coefficients for this grid voltage to plate voltage curve that I have. For every grid voltage, every one of these intersections, I know a voltage for the grid, I know a voltage at the plate, and I can use that same line of best fit and generate a final set of coefficients. So now, all along that load line, based on what the grid voltage is, I can compute what the voltage is at the plate. And this winds up being a really, really powerful tool. Comparing the results of the equations to some actual measurements on a triode. So I've taken my grid and plate voltage equation that I've got here. I've plugged those coefficients into this equation, and I've just given it a representative sine wave. And the output winds up being this inverted sine wave, and it's more pointed at this lower end. And notice how it kind of tapers off and flattens up here on the top. And that falls directly out of this polynomial equation here. Given a grid voltage, it gives me a plate voltage. Now, comparing that to some actual measurements taken from the 7-pin tube test harness, you can see that same sort of inverted sombrero shape here, where I've got a pointed downward end of my sine wave here and that slightly flattened top half. And this is a visual representation of the asymmetrical clipping that a triode is so well known for. But now we've been able to actually step through the curves on the tube datasheet, derive an equation that actually defines the nature of that asymmetrical clipping. So in what is possibly the most boring video I ever hope to upload to YouTube, I've walked through the steps from a datasheet for a triode, and I've managed to pull out a formula that relates the plate voltage to the input grid voltage. So what? Well, when I discovered this a year ago, what was so cool about this, I was trying to come up with a way to emulate any tube amp that I could dream of. So I wanted to be able to take a schematic of something like a Marshall Plexi or a Dumble or a Fender Princeton. I wanted to be able to take that and put some mathematical models in for the different tubes and come up with a way to emulate the sound of an amp just based on what the schematic was. Now, I know there's other tools out there that will do this, but going through the process and reducing an amplifier and an amplifier schematic down to some math and a series of equations, I suddenly have options. I can write software to do this thing from beginning to end. I might put all of that stuff into an Arduino, or I might be able to come up with some circuit that's an analog computer, like a ring modulator, that does multiplication and emulates something from an analog circuit. So it's a really, really powerful tool. And that's the reason why I wanted to tell you guys about this, and also why I want to make the Excel spreadsheet available to you guys, because maybe one of you guys can come up with a tool or a piece of software to design amplifiers or emulate amplifiers, any kind of cool thing like that. Anyway, it's out there. Go download the Excel spreadsheet, see what you can come up with, or just download it and play around with it and say, wow, isn't that cool? And then never think about it again. It's up to you. As for me, my next step is I'm going to try to put that equation into the ring modulator or a ring modulator inspired circuit so I can do that mathematics to emulate the formula that is a triode gain stage. Anyway, we'll see you next time.